All right, I have double checked, and I definitely have the microphone on this time. So I'm going to try to run through this. If you want to, you could watch it on mute and just get the information if that's what you desire. But what I'm going to do, I'm going to try to just change the colors up as we go so we know which ones we did. Number one, how to find the gauge pressure. So gauge pressure, if you'll remember, is just rho GH. This is density, and this is gravity, the acceleration due to gravity, and this is the height below the surface of the fluid. And G is always 10. So if you want to do absolute pressure is the gauge pressure plus the atmospheric pressure, and that pressure is 101,000 kilopascals. So that's the difference between the two. Number two, how does temperature affect how is temperature related to the kinetic energy of molecules, the speed of the molecules? So temperature is directly proportional to the kinetic energy of the molecules, and temperature is proportional to the velocity squared of the molecules. So essentially, if you double the temperature, you double the kinetic energy. But if you double the temperature, that would be proportional to the square root of 2 of the velocity, because you're squaring it, and the square of square root is 2. So you'd end up with a 2 in front. So just keep that in mind. If it's asking you for the connection between temperature and kinetic energy, it's direct. Whatever happens to the temperature happens to the kinetic energy. If you're asking about temperature to velocity squared, remember that square term's in there, so you have to be a little bit more careful about which one you do. If you double the velocity, you quadruple the temperature, because again, that's squared. Also remember this mass is in here. So if two different types of molecules have the same temperature, they'll move at different speeds depending on which molecule is heavier. The heavier molecule doesn't need to move as fast to have the same kinetic energy. So this is the formula for kinetic energy. And then also remember that temperature is proportional to the pressure times the velocity. So if you're discussing one of those pressure versus volume, I said velocity, I apologize. If you're talking about one of the pressure versus volume graphs that we did so many of, the pressure times the volume is proportional to the temperature. So a change in the pressure versus volume would reveal a change in the temperature, which in turn would reveal a change in the kinetic energy. All right. So know how to construct an FBD. Know how to construct an FBD with buoyant force. So the key thing that I think most people leave out here is if you have a buoyant force, so like if we're talking about a boat or something, you would have like the buoyant force on the boat, and then you would have the force of gravity of the boat, and then the force of gravity of the stuff in the boat. So for example, if you have a 500 kilogram boat, you would need to do mg for the boat, mass times gravity for the boat, that's the force of gravity. And if you had stuff in the boat, like say 2 people that each weighed 100 kilograms, you would have to do 200 kilograms times g as well. And if it's a graph or a picture, all of these forces should balance out, meaning that the ones up should balance out with the ones down if it's at rest. And then on the other side of this is the one that I think gets us a lot of the time, and that is like for the air in a balloon, or like a dirigible or a blimp or something like that. The buoyant force is upwards, and then you have the force of gravity on the balloon, but then you also have the force of gravity of the gas in the balloon. You can't forget about the force of gravity of the gas in the balloon. If you're trying to find the force of gravity on the gas in the balloon, you often have to do the density of that gas times its volume times g. And that usually gives you the weight of the stuff in the balloon, because density times volume is mass, and mass times g is the force of gravity. How do you find the electric force? Give me 2 ways to find the electric force. So the electric force can be found 2 ways. The first way is to do kq1 q2 over r squared, where this is charge 1, and this is charge 2, and this is the distance between them. So I do want to point this out because this is something a lot of you made a mistake on the test. This r stands for distance. It does not stand for radius. So you don't have to cut the distance in half. So don't do distance over 2 is equal to r. That's not right. It's just the distance between them is equal to r. All right, and the other way to do it is Fe is equal to EQ, where E is the electric field. And remember that the electric field can be written as V over M. And if you wanted to find the mass of the object or the acceleration of the object, you would take that electric force and then put it into the F equals ma formula. And usually, like most of the time, they're either going to give you the acceleration or give you the mass and ask you to find the other one. So you're using one of these two formulas to find this, the electric force, and then you're using F equals ma to find the difference between them. Or sorry, to find the variable that you're looking for. Okay. How do we figure out where an electric field is the strongest and where is it the weakest? So if we want to figure out where it's the strongest, it's where the field lines are closer together. So if it's like a uniform electric field, if it has field lines that are more tightly packed, it would be an example of a stronger field. So this one's the stronger field, tighter packed lines. If you're looking at a field line for this, then the electric field gets stronger as you get closer to the particle because the field lines are closer together at those points. As you get out farther and farther away, those field lines spread out, and as they spread out, the field gets weaker. All right, so moving on. Know the properties of ideal gases. So there should be 5 things. There's technically probably more than 5 things if we're being honest, but for the sake of this, we're going to go with 5 things. So the first thing that should be noted is that they are random in motion. So they have random motion. There's nothing guiding them. They're just bit-bopping about like, particles in air. I suppose the best way to think about it is if you think like about throwing a load of tennis balls into a room, and then like once you throw them, they're just kind of moving at random. There's no real way to predict what any individual tennis ball is going to do. You have to kind of look at them as a whole. The other thing is the volume of the particle has to be much less than the volume of whatever it's in. So this sounds kind of weird, but it makes sense. Your particle has to be small enough that the container it's in is significantly larger by a large order of magnitude. For instance, if I think about a hydrogen molecule in a beaker jar, the hydrogen molecule is on the order of like times 10 to the negative 20th meters in diameter, and the other thing is a 1/10 of a meter in diameter. So they're significantly larger. It basically means you can't have a container that's the size of the molecule or near the size of the molecule. Number 3, they have to obey Newton's 3 laws. That's the assumption that's being made, is that they're obeying all the laws of Newton. In other words, objects at rest tend to stay at rest, objects in motion stay in motion, F equals ma, and the third law, every action has an equal and opposite reaction. Number 4, they are elastic collisions with no energy lost. So whenever the particles collide with each other, you don't have like any like heat formed. They're just colliding and bouncing off each other, just kind of like idealized billiard balls on a billiard table. No energy is lost in the collision. And then finally, you're not adding any outside forces on the system whenever you're dealing with an ideal gas. All right. How mass and velocity both affect kinetic energy? We talked about this a little bit earlier. Whoops, I didn't mean to duplicate that. We talked about this a little bit earlier. So whenever we discussed this earlier, we said that the mass is directly proportional to the kinetic energy, and the velocity is squared proportional to the kinetic energy. And I suppose another way to write that is that the velocity is proportional to the square root of the kinetic energy. The important thing to know there is that if I double the mass, I'm going to double the kinetic energy. But if I double the velocity, I'm going to quadruple the kinetic energy. If I double the mass and double the velocity, the mass is going to double it, the velocity is going to quadruple it because 2 squared is 4, And so you'd end up with 8 times the kinetic energy. All right. What are the really small forces that cause air resistance to work? All right, so this is kind of one of those like stupid little things that comes up like once a test, it seems like, on the AP test. It's a stupid question because to me, I don't know, it feels like you're reaching on the actual meaning, but technically this is right. So what are the small forces that cause cause air to resist motion? So the drag forces on things. So if you run your hand through the air, what's that feeling? What causes that feeling that feeling of resistance that you feel? And that's the electrons of the molecules repelling each other. So basically, like on a technical level, the electrons in the outside of your hand as you sweep it through the air are being repulsed by the electrons that are existing in the air molecules, and that is what causes the drag force. It's kind of the obnoxious argument that we don't actually touch things. So if you've ever heard somebody say, well, you're not actually touching anything because the electrons are repelling each other. It's that. So it's kind of a silly little argument, but nonetheless, there it is. Okay. How do you determine the density of a fluid using the buoyant force? All right, so let's see. Let's change. I haven't done orange yet. Okay, so the key thing to remember is that density is equal to mass over volume. That's the first thing. And then remember that oftentimes whenever we're dealing with these, the object is at rest. So you have like an object sitting in water and it's at rest. And so the density of the object and the buoyant force should be equal to the force of gravity. So remember we talked about this earlier, that if you want to find the mass of an object, you can do density times the volume. So density times volume, this gives us our mass. And then if we multiply it by g, that gives us the that gives us the force of gravity. And then on the other side, we have the buoyant force. Remember, buoyant force is the density of fluid, the mass of the fluid you displace times g. So to find that, we need the density of the fluid and the volume of that object that is submerged. And so notice here that the g's cancel each other out. And what you're left with is this first formula is basically the density of the object times the volume is equal to the density of the fluid times the volume submerged. So if you know the density of the object and you know the density of the fluid and you have those two volumes, you could find it. And then notice the other way to do this, you could rewrite volume as equal to area times height. And if you have if you have the height, you could figure out the height submerged. Those areas cancel out. And so you could do it that way. Now, I also want to point out that you could, theoretically, instead of having to do this, if they gave you the mass of the object, then it would be mg. You would just skip the volume of the object. Mg is equal to the density of the fluid times g times the volume submerged. And then that would give you could find the density of the fluid that way, right? If they gave you m, you could find it this way. You could just solve for the density of the fluid, just divide everything and get it to the other side. All right, here we got some short ones. They may not be quite as short as I gave them room for. I do apologize. I think last year I just kind of talked about it with them. I didn't actually go through it, so I think I ran out of room a little bit. I think this was more last year, just like here, know these things, but I'm trying to go through this with you guys. So Bernoulli's equation is essentially an expression for what formula? It's energy for fluids, right? So you've got P naught plus rho GH plus 1/2 rho v squared, where this v is for velocity. And so this one is connected to kind of like the kinetic energy of the fluid. This one's the potential energy of the fluid. And then this is just the energy the fluid has. I think that's probably the best way to think about it. The pressure energy, maybe. So this is like U. Also know how to check and draw an FBD on a variety of different situations. So the key thing is the thing that I kind of want you to note here is things to look for when you're trying to check FBDs. So when you're doing one of these and you're trying to check to see if the FBD is correct, there's a couple of things to look out for. And this is by no means an exclusive list, but I think it's useful. Double check to make sure the size of the vectors are the way it's supposed to be. For instance, if it's supposed to be balanced forces, double check that those forces are indeed balanced. And if it's supposed to be accelerating, double check to make sure that one of the forces would be bigger than the other. Also check the direction. For example, gravity. If they show gravity going up, that's wrong. Gravity should be down. If they show the buoyant force going down, that's wrong. The buoyant force should be going up. So like double check those directions and make sure they're going appropriate to the way it is represented. Okay, things to know. Know things necessary to calculate Bernoulli's law and how it affects speed. So let's see, I kind of wrote on the side here. And so we're going to come back to it. All right. I'm going to change it to, let's go with that. All right. So the essential thing you need to know here is that if you have a fast velocity, you're going to have a low pressure. All right. The important thing to note is that if we have a lower velocity here and we have a higher velocity here, we have to have them equal on both sides. So assuming that the U formula doesn't U part doesn't change, the potential part doesn't change, then if this goes up and this, if this goes up, then this would have to go down in order to maintain equal on both sides. It's also important to note, maybe like this, I guess this one kind of goes with the next question too, because they're kind of connected. Be familiar with the continuity equation and how it affects speed. Briefly, just note that, like, for example, A1V1 is equal to A2V2. This is area 1 times velocity 1 is equal to area 2 times velocity 2. Again, note if you change the area, that's gonna either increase or decrease the volume, which could in turn increase or decrease the pressure. A smaller area means you're gonna have a bigger. What was I trying to write here? I'm sorry, I did this last time. Oh, sorry, these are divided into. My bad. This goes together, and then this goes together. So smaller area, faster velocity, lower pressure. Bigger area, slower velocity, higher pressure. All right. Also note that the area of a circle, which is what we're typically dealing with, is equal to pi r squared. And so the proportions get messed up if you're dealing with the radius instead of the velocity. So instead of it being AV1, it's R1V1 and the R is squared equals R2V2 and the R is squared. All right. And just kind of note that changes the relationship. So if you double the radius, you have to quarter the velocity. So essentially, if I do 1 times 1 on this side, and then I double the radius, I have to 1/4 the velocity to make it still equal 1. So just note that the radius has a square relationship. What are action-reaction pairs? Okay, so this is the part that often gets kind of annoying because it's just, they seem a little bit, I don't know, they seem a little pedantic, but they are questions that are definitely going to be asked. And the key thing to action-reaction pairs is that they have to be equal and opposite. That's part 1. All right, that's the part that everybody remembers, and that's good. That's what it is. But it has to be on 2 different objects. So that's the key. It has to be on 2 different objects. So if you say the electric force, right? If you say the electric force is an action, the electric force on object 1 would be the action. The electric force on object 2 would be the reaction, right? So like the electric force of 2 on 1 is the action force. The reaction force would be the force of 1 on 2. Whenever you do gravity, the force of gravity, the reaction force, if the action force is the earth pulling you down, the reaction force is you pulling the earth up. They're a little bit weird. They have 2 different objects. That's the key. Equal and opposite, 2 different objects. All right. Be familiar with P versus PV graphs. So how do you find the relative temperatures? Remember, that V is volume. So here the V is volume. All right. So How do you figure out relative temperatures? Compare P1 times V1 and P2 times V2. Whichever one's greater is the greater temperature. If they're the same, it's the same temperature. How do you find the internal energy, or what happens to the internal energy? Internal energy is equal to 3/2 N kBT. If you need to figure out what happens to the internal energy, look at the temperature. If the temperature changes, your internal energy is changed. How do you tell if heat is added, work is done, or energy is changed? So work is done is fairly easy. There's area under the board, under the line. If there's area under the line, work is done. Energy is changed. Then that means that the temperature is changed. So the easiest way to see if heat is added, and this is not the only way that heat can be added, but you definitely added heat if you did no work and the energy changed. So if the energy changes and there's no work being done, like a vertical line, then heat has either been put into the system or taken out of the system. And how does temperature affect internal energy? It's a direct effect. If you double the temperature, you double the internal energy. And how do you define the work done? You find the work done by doing the area. So for that last part, I'm going to bring us down, and I'm just going to ask you to look at, this stuff that we did on the way last time. All right, so just kind of give this a quick look-see. Make sure that you know these. If the pressure and volume PV goes up, temperature goes up, potential energy goes up. If pressure, volume go down, temperature goes down, internal energy goes down. I said a potential. That's internal here. All right. You have positive work if you have a negative change in volume, and work is done on the gas. Work is negative if you have a positive change in volume, and work is done by the gas. All right, these are just real tricky. Make sure you know those. Work for a section is the area under the line. Use these rules to ensure that work is in the correct direction. Area inside the box is the work for a process. If it's counterclockwise, work is done on the gas. If it's counterclockwise, work done on the gas. Clockwise, work done by the gas. And remember that work done by the gas is negative and work done on the gas is positive. And then just kind of remember these things. Isothermal, usually a curve, temperature stays the same, no change in internal energy. Whatever work you did was done to change the heat of the system. Isobaric means there's no change in pressure. And isochoric means that there is no change in volume. And when you have an isochoric relationship, the change in heat is equal to the change in internal energy. And adiabatic is there's no heat exchange. The only time I ever see adiabatic come up is when you have to know this, that there's no heat change. I think that's the key thing. Okay, moving back. All right, so 17. How are temperature and pressure related? We've talked about this before, but temperature is directly proportional to pressure times volume. So if I change the volume, I need to have a difference in pressure. So if I change the volume, I need to have a difference in pressure. And if I change the pressure, I'm going to change the temperature. So for example, if I have a box at a pressure and a volume, and then I double the volume, that's going to decrease the pressure, which should lower the temperature inside of it. Vice versa is also true. If I decrease the volume, that's going to increase the pressure, which should increase the temperature. All right. Be familiar with the formula for conductivity. This is the formula for conductivity. You just need to be able to use it. So Q, remember, is heat. So this is heat. I cannot spell. Heat, time, and this is the rate of heat flow. You might see this listed as flow of heat, or heat flow. I'm trying to figure out how else they would say it. Rate of heat exchange. All right. This is a K. This is my superior way of writing a K, and it's a constant for a given It's a constant for a given substance. So every substance is going to have its own conductivity constant. This is the area, and this is the change in temperature. And finally, this is the length that you are trying to transmit the heat down. Okay, let's see. What does convection, conduction, and radiation look like graphically? So the key thing with conduction is that it moves from hot to cold. So substances have, if you're conducting heat, the heat has to move from the hot end to the cold end. There's no way for the cold end to get to move from cold to hot. It always moves from hot to cold. For convection, that one is the cycles where you have hot up and cold down, cold air sinks and hot air rises. All right. And then lastly, we have radiation. Radiation just means the heat is radiating out in all directions. And so, like, if you see heat flowing outwards, evenly spaced in all directions, that's radiation. All right, what is entropy? Entropy is the measure of disorder in a system, and it will increase with time. So the longer that goes by, the more the time is going to change. The more the time changes, the higher the disorder in the system. So if you start off with a fairly ordered system, for instance, you have hot particles on one side and cold particles on another side of a room, as time moves on, the particles should get intermingled and it should become more and more disordered until you cannot tell where the hot particles and the cold particles are. All right. Also with entropy, just as a reminder too, you have to exert energy to lower the entropy of a system. So if I want to lower the entropy of a system, I have to do work. That's the point of a refrigerator. A refrigerator is lowering the entropy of a particular area. And a final thing of note is there's no way to lower entropy of a particular area without raising the entropy of the universe. So when you have a refrigerator running to lower the entropy inside the refrigerator, it raises the entropy of the universe because it puts out heat on the backside of the refrigerator, which causes particles to move around more rapidly. How does heat move? Heat moves from hot to cold. And this is I'm going to use the word jiggly too much here, but that's okay. So jiggly particles jiggle less jiggly. So jiggly particles run into other particles, and then they keep jiggling until they jiggle less jiggly until the particles are all equally jiggly. All right, so you get lots of jiggling. So you have very rapidly jiggly particles that collide with not so jiggly particles, and it causes them to jiggle a little more, and then that process gets transferred on down the line until all the particles are at roughly the same jiggliness. I think that's good. Be familiar with the FBD on a piston. So the key thing to remember on a piston, this is something that you probably would forget if we didn't talk about it. You have a force upward from pressure that's caused by the gas. You have a force downward from gravity of the weight of the piston. And then you finally have the force of atmospheric pressure on the piston. You can't forget that one. That's the one that we always forget, or at least I always forget, is the atmospheric pressure on the piston. Remember, if you're trying to find force for a piston, like forces are equal to pressure times area. So that also might be useful to know for both this guy and for this guy. How does a grounded object respond to a charge? All right. So if you have a grounded object, it means that electrons can flow into or out of that object. So it pulls electrons in if brought near a positive charge. So if you have a charged object and you bring it near a positive charge, the grounded object will pull electrons in to make it more negative. And then if you remove the ground, that is now a negative object. And then if you bring a negative charge near them, it pushes the electrons out. If you remove the ground, that would be a positively charged object now. All right. I have no idea what I meant by 25. I tried to figure out what I meant by 25. I don't know what I meant by 25. I'm really sorry. I'm sure it had a reason. I think 25 and 26 are connected, if I had to guess. And both the electric field and the electric force would have similar graphs. So you could have FE, or you could have the electric field. Either one of these should be the same because the formula is KQQ over R squared or KQ over R. You can, over R squared. In both instances, the distance is squared on the bottom, and so that results in graphs that look like either one of these two, depending on whether you're graphing versus distance or graphing versus distance squared. Okay, How do you determine the direction of an electric field or a force? How would an FBD look like with that in mind? So for a field, the field always goes towards negative charges and away from positive charges. So if I have a negative charge here and a positive charge here, that would create a field that looks like this. It would also loop, and the field would go in the same direction. Force likes repel, opposite attract. So when you're drawing your FBD, make sure that you draw the lines indicating the direction that it would feel the force. It should be towards it, towards the other charge if they're different, and away from the other charge if they're alike. When looking at electric force, how is it applied to both charges? It should be applied equally to both charges. Know how to find the electric force in the hanging balloon problem. Let's skip that one for right now. What is necessary to find the electric field? You need one charge and one distance, and if they're that's how you would use that formula. So I need one charge that goes in for Q, and I go one distance that goes in for R, and then I could figure out the electric field. Or you can use the force over a charge. In that case, you need a force and a charge. So an electric field can be this formula, or it can be this formula. Both are equally valid. It just depends on the situation they have provided. All right, balloon problem. Okay, so here's the situation. We have a rope with tension. You got a balloon that's negative. It doesn't have to be a balloon. It could be anything that's charged, but a balloon is just easy to figure it out. So you got mg down, you got the electric force out, and you got the tension up and at an angle. And here we have a negative charge, so we're assuming it's being repelled from the other negative charge. All right, I gave you an angle here. So what you can do is you can set up this triangle where you have tension on the red line. I did that stupidly because I have a blue letter, but whatever. The tension's the red line, mg is the purple, and fe is the green line. Because the tension has to cancel out mg, that's why this is mg, and it has to cancel out fe, that's why this is fe. It's got to pull to cancel those two out. And so what you can do with this is you can do mg is equal to mg over fe is equal to tangent theta, because this is the adjacent side and this is the opposite side, and you can solve for fe. Once you find fe, if you wanted to, you could do k q1 q2 over r squared and solve for one of the charges. If both charges are identical, this could become q squared. All right, so a couple other things. Conservation of charge. Please note that if you have three objects, I didn't do a good job here. There we go. If they're the same size, I guess I could just duplicate them. All right, and this has 1, 2, 3, boom, 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 4, 5, 6. All right, 7, 8. There we go. So if I touch these two together, boom, touch them together. Okay, what happens? Well, I'm going to split half of my charges are going to get moved over here. All right? So then what happens if I then touch this guy? All right, now half of my charges are going to go into this guy. And the key thing should be that you end up with the same total amount of charge that we had at the beginning. So we had 8 charges at the beginning. We have 8 charges now. Now they're just spread across. This is true if they're the same size, shape, and material. If they're not, it might be a little funkier. The charge should still be conserved. If you have a smaller object, like let's say that, let's say that I touched this guy. Whoops, let's go. Okay. Dadgum you. Okay. Let's say that I bring this guy in and we touch, boom. All right, it may not get all the charge. It may just have one charge go over. All right, so if they're not the same size, it's not necessarily going to be like that, but like you can kind of do it intuitively. If they're all the same size, when you touch them together, it should split. If they're not the same size, then the smaller one generally will get less charge. All right, polarization. So something just to note about polarization with the balloon, we had a negatively charged balloon, and for instance, we brought it into contact with a wall that was neutral. So what happens is in the wall, you get a polarization of charge where the positive charges move to the forefront and the negative charges get repelled, and you end up with a temporarily polarized wall. And the same thing's true if you do this with anything. So if I have a balloon that's negatively charged and I bring it into proximity to a bunch of little papers down here on the ground, then those papers, if we zoom in on the paper, whoosh, if I zoom in on these papers, then the positive charges and the negative charges and the positive and the negative and the positive and the negative, positive, positive, negative, negative, they're going to align so that they're attracted to the balloon. By the way, once these touch the balloon, they're going to try to discharge to make it neutral. And so if I bring one of these up, it's going to probably, once it touches, boom, it's going to lose its positive charges into the balloon to try to neutralize it. And then now this is negative, so it's going to repel away. All right. Sometimes, like if you're using a balloon, the rubber kind of makes it stick a little bit, but that's generally what happens. All right. Last, this is where I saw some mistakes on the test that we just took. I just want to point it out. So if you have, oops, here, let me back this out a little bit. Here we go. All right, so I have 3 charges here. All right, I'm gonna just kind of change the style here so you can kind of see them a little bit better. Since I'm not reading them, it becomes a little bit more difficult. So I've got a there we go. So I've got 3 negative charges, and let's just, it doesn't really matter right now if they're equally spaced or not. But what I do want to point out is that there's going to be an electric force that this one feels from this guy, right? This guy right here, all right? And there's going to be a force this way that he feels from this guy right here. Now, the mistake most of y'all made on the test, a lot of you made on the test, was you said this was equal to 5. I'm just making up numbers. We say this one's equal to 7. Y'all just said 5 plus 7 equals 12, and that's how much it felt. But you can't do that. It's vector math. So you have to break this into components, right? And so what we have to do is we have to say that f2 times y is 2 and f2x is 4. It may, like, it's not to scale. Just kind of roll with me here. But what that ends up doing is I have to break it into components because I've got an x direction and a y direction. So you have to break it into components. If you know this angle, that's helpful, all right? So if I know the angle, I can break it into components. Remember that the x component is usually the force cosine the angle. Y direction is f sine the angle. You have to break it into components. Once you break it into components, now you can do this. You can do F1, because it's in the x direction, plus F2 in the x direction. You would only do this one. All right? Let's change the color. You would only do this one. And this would go here, and this would go here. You would add those together to get the total force in the x direction. And then in the y direction, you might have to add them in the y direction. In this particular scenario, we don't have anything in the y direction. We just have this guy. So this would be our force in the y direction. And then once you do this, now you can take this, put it in here. You can take this and put it in here. And then now we can do the Pythagorean theorem to find the net force acting on the object. All right. I think I summarized all that. I know that's a lot, and I will do my best to do any clarifications that need to be done in the little review session, hopefully on Monday.